Okay, good. So I talk about from the nuclear structure, from neutron halo to tensor forces. When we discovered neutron halo, we thought this is new type of nucleus, and nuclear structure is different from different ones. And while we are studying this, we have the many questions, and solving one makes another questions and comes. And finally, we had big question that is related to the stable nuclei. As a matter of fact, it's a mirror of the stable nuclei. So you have to understand stable nuclei, phenomena in stable nuclei to understand the neutron halo. So I want to connect that in this talk. So essentially, okay. So neutron halo, I don't repeat many details of things at all, but essentially it's low density and weak binding neutrons that is sitting around the core of nucleus. And it is an object that's very loosely bound. So you have to discuss the structure of that. You cannot forget the continuum. You have to discuss bound state and continuum at the same time. And also there's very funny structure in lithium-11 and some other halo nuclei. It's called bromium. This forms a three-body system, but none of two makes any bound state. And this is very unique binding system. Only in quantum mechanical system, bromium is observed only in nuclear, and no other object like molecules and such things. It has not observed. But one of the main thing that I want to connect to my talk today is that neutron halo in lithium-11, we study the wave function, and then they are mixture of P wave and S wave, almost half and half. And actually, if you see usual shell model picture of P shell and ST shell, that P1/2 and P3/2 makes one major shell, and S1/2, in this case, I'm talking about 1s/2 state, those are in different major shell. So those two different shells and orbitals are mixed 1-to-1. Why? And this question really hit me very strong. And to answer that, there's a lot of discussion in theory, and I will show you later, almost at the end, that this really gave us new view to the nuclear structure. And so actually in halo nuclei, by some reason, S1/2 orbital plays important role near the southeast corner of P shell, in P shell region. But similar irregularity occur near the southeast corner of ST shell also. You know that the anomaly of this disappearance of the magic number 20 and such things. It's also southeast corner of the major shell. And another long-standing question, and I don't think none of the effective theory can solve this, is that the effective interactions that explain carbon-12 ground state and carbon-16 ground state simultaneously doesn't exist. I mean, no one knows yet. And I don't think any real ab initio calculation like green function Monte Carlo didn't reach there yet. And we don't know this question. We cannot answer this question yet. And then another thing is the tensor force we know that is an important force from pion exchange interaction. This is essential interaction for making a binding in deuteron and helium-4. That we know from real ab initio calculation. But once we go to heavier nuclei and talk about the shell model, we don't treat them explicitly. There are some trial now from the based on shell model, but there's no real treatment of tensor interaction yet. Okay, so this is one most striking result for me, is that first of all, this momentum distribution of fragment of lithium-11, lithium-10 has very peculiar momentum distribution. It's here. And this momentum distribution of the fragment can be explained only when you assume S wave and P wave mixture. So this is one evidence. And then beta decay in 1970, also they observed that S1/2 wave is mixed with 30 to 40%. And this is also 1-to-1. Another experiment is transfer reaction in Triumph, that to explain angular distribution of the transfer reaction, PT reaction, you need S wave and P wave in this amount. So why such a separated orbital in normal shell model mix so strongly? It's 1-to-1. So then I repeat this. You see that some anomaly, we see many anomalies in neutron-rich nuclei since the radioactive beam experiment. Here, like broken N=8 magic number and halo, and helium-10, and naively it's doubly closed shell, but it's not bound. And seems like N=6 is a magic number. And here you see that this is corner of SD shell. Then you see that nitrogen-16 is, neutron-16 is a magic number, as well proton-16 is. And this part, N=20 disappears, and oxygen-28, again, is expected to be doubly closed shell, doesn't bound, it's not doubly closed. And so on. It's always in this corner, something happens. And okay, so I just repeat the same thing that I plotted here, and I'm gonna try to explain those things later from one principle. Okay, then look from the tensor force that we very well know that D wave in deuteron in naive in a shell structure or whatever, if you may put two nucleons, it starts from S wave, but the deuteron need D wave definitely, and helium-4 include D wave. Another thing important is that the saturation of nuclear matter and nuclear density are very much related to the tensor force. So tensor force is there to bind nuclear matter and nuclei, but then there must be some Pauli blocking in the space, in configuration space. And this Pauli blocking is making nuclear saturation, density saturation, or energy, binding energy saturation. I will explain this a little later for nuclear structure. And so after that, then I want to show you what is the effect of tensor force on nuclear binding itself and shell structure. And then if you understand this how tensor force gives the binding energy to the nucleus, then you will see the difference of binding of stable nuclei, or N equals Z nuclei, and very neutron-rich nuclei are very much different if you see from the viewpoint of tensor interaction. So that's a very important point. And one very important point is this tensor force I'm going to talk is a little different from usual nuclear force, nuclear treatment of nuclear wave function. That for deuterium and helium-4, our initial calculation include the wave function of proton and neutron with very high momentum tail. I mean, short-range correlation and tensor correlation, everything is included. There, definitely we know a lot of binding is available from tensor interaction. But if you go to the shell model space is roughly limited to the Fermi momentum. So momentum space in the wave function is restricted in shell model. So it's almost always low momentum space in nucleon. But when I have to talk this basic tensor forces in nucleus, I cannot forget the high momentum component of nucleon in nuclei. In such high momentum nucleon exist in the ground state of nucleus. That is a very important question. And theoretically, of course, it's known in helium-4 and deuteron. And do they exist in other nuclei? That is the important question. So now, between halo and new shell behavior of nuclear ground state, and this high momentum nucleons produced by the tensor force, is there any relation? So that's a question. And my answer is yes, they are directly related. High momentum nucleons are not just some Q space disappeared from spectroscopic factor. It really affects the binding of the ground state of the nucleus. So that's the goal of my talk today. Okay, so sorry, you know this very well, but I have to repeat because I want to stress on some points. So this is binding of deuteron, and interaction has, pion exchange has central interaction that has short-range repulsion and tensor interaction. And if you calculate the binding energy of the deuteron, it is separated into like this. It's kinetic energy, of course, it's positive. And then the central force gives you this binding energy. And mostly comes from S wave diagonal part, and some contribution from D wave. Now, because of a tensor interaction, it gives much more binding energy and less interaction. So if you add those three, compensate the kinetic energy, and finally get the binding energy. Okay. But now, interesting thing, that tensor interaction comes from D wave. We always say D wave, but it's not the D wave. This is transition from S wave to D wave gives the binding energy. So it's a transition energy that is giving the binding energy. It's a very important thing. Okay. Now, another thing is, if you see the size of this wave, S wave and D wave, it's funny that D wave here is smaller that means this D wave include high momentum. So if I write it in very maybe misunderstanding way, but to show it well, you know that you have S wave to proton and neutrons, but when you make a transition to D wave, it's transition. If you make a transition D wave, this transition makes high momentum. So actually, it's like this D wave, nucleons are bound in much narrower potential than this. It's just like that. So to make this one, you really need high momentum component. And same is true for alpha particle, and it's more complicated, of course. But then this is the binding energy diagram for helium-4 for this calculation. Here it is interesting. Of course, this is the excitation, transition energy. Proton and neutron are excited to D wave or maybe higher waves and many waves. And this shows the convergence of the energy. So you have to include many transitions to upper state by this proton and neutron pair. Tensor force interact only proton-neutron pair, not neutron-neutron pair and proton-proton pair. And so to converge to this energy, of course, it's going, you have to go like L higher than delta L 8 or so. But important thing now I want to say that even if you include only 1L transition, 1L transition is essentially, this is one major shell transition. If you have one major shell include one major shell transition by this tensor interaction, then you already gain almost 13 or 14 MeV binding energy. And if you include 2L, so it's essentially two major shell, then you gain more than 30 MeV by that. So this is important thing. It is especially important for my talk today that only one major shell transition already makes binding of 13 MeV. It's a big energy compared to the shell gaps and such things. Okay, so this is essentially very important things we learn from helium-4 rigorous calculation. Okay. Now, so we believe, now I go back a little bit, because those calculation has been done that I think the best of initial calculation is done by Argonne. And I don't want to explain anything about this, but the most important result they got is most of the binding energy of the nucleon is from pionic pion. So pion dominate to make the binding of the nucleus. This is a very important result. So this just support the following discussion where I discuss based on the pion exchange interaction. Now, tensor, what is tensor interaction? Tensor interaction is this. In pion exchange, there is central force and tensor interaction. Tensor interaction part is like this. It depends on the Q square. So interaction becomes stronger if you have larger momentum transfer. And this is spin and angular momentum factor. And this is because pion is Schultz scalar particle. Now, the point is, this tensor force gives strongest contribution when you have two pion exchange. The reason is that if there's only one pion exchange, those line is same, just momentum conservation, that you cannot exchange much high momentum. So Q is near zero, except the exchange term, but exchange term is differently treated. So essentially, with one pion exchange, momentum transfer is small, so that the tensor interaction effect is small. Now, if you have two pion exchange, here you have just the inner line. This can be any momentum. So this can be very high momentum, and that can give much more binding energy from tensor interaction. So the essential thing is this diagram. Okay, there's some line in here. Now, it just for later discussion, just remember the selection rule. From here to there, because this is 0 minus, it has to be, of course, delta J has to be 0, delta S equal 1, and delta L equal 1. Delta L has to be 1 or more. I mean, this is minimum, but it's, so if you change the L, you have to change spin. Okay, so this is a selection rule for this one particle. But selection rule for this state to this state, two particle state, from this one to this one, is the delta J equals 0. You don't change delta J, and delta L is 2. So this is a D, I mean, in the neutron case, it's D wave. And then also same, spin has to change by 2. So this is selection rule, just remember, okay? Now, recently, Osaka made this shell model approach to the tensor interaction. What he did is he used only this. So in shell model, the many particle exchange is just replaced by G matrix. G matrix is one effective interaction, but the point is there's no inner line. Okay, so that's a really important part. You can make effective interaction, but without this high momentum nuclei. Now, but Osaka found that there is an effect. You can make little higher momentum transfer by making an exchange term. So he calculated this exchange term in the shell model base and discussed this effect of tensor coupling between orbitals. And then that has a great success. But this is a part of the tensor effect of the tensor interaction. It's not all. So it's really different if you see this diagram or this diagram. Okay, so in the following, I discussed based on this one. And I discussed many times with him what is the relation of what I'm doing and what he's doing. Is what I'm discussing is inclusive of him, or is something different? Because there's no rigorous numerical calculation, we cannot decide at this moment. And shell model has very good calculation, but this type of calculation is very difficult and time consuming, and it's not done yet for heavier nuclei. Okay, for example, this is a mixing of those higher state. for example, for helium-4, this is n=1 transition. So you see that the mixture, original particle is 4 neutrons, 4 nucleons, 2 protons and 2 neutrons in S wave, and 2 of them are excited to higher state. And this is the excited state. So it is really a mixture of many excited states up to very high things. But the main part is here. So it's essentially making that, filling that selection rule. You have those mixing. And so, but this is just filling. So essentially, this Myo, Kato, and Ikeda, those persons made a model that they put the wave function of helium-4 as this really ground state configuration and 2-particle excitation. So they essentially made all mixing to very higher excited level, but this is just I just picked up only one higher of 1 h bar omega excitation. So there's an excitation like this. It's here. This 3 is this coupling. So 2-particle goes to p1/2 state and couples to spin 1 and I spin 0. So this is this configuration. So essentially, those 2 nucleons make spin flip, go up to p1/2. Now this one is opposite, spin 0 and I spin 1. This. And so number 4 is this excitation to p3/2, but in little funny spin configuration. And this is other spin configuration. So those configurations are included and calculated the binding energy, including central force and tensor force. Now, this is the energy obtained by the tensor interaction. And you see that essentially this one gives almost all the binding energy from tensor interaction. So that is very important. There are many states can mix based on this 2-particle, 2-hole excitation, but the main configuration that gives binding energy is this configuration. And you remember this configuration is exactly filling that selection rule. You change spin 2 because this is +1 goes to -1, and L changes 1 for 1 particle and L changes 2. So this is essentially delta L equal 2, delta S equal 2, and spin change is 0. So that's the tensor selection rule. So this one is really giving the binding energy. So that is the fact. And for one major shell transition. Okay. So this is next one is the important thing is this one. Next major shell, but largest spin, largest J orbital is not really used by the tensor interaction. That is because just the selection rule that pseudoscalar pion exchange cannot change J. Okay? So that's why this contribution is weak, not 0, but it's very order of magnitude weak compared to this one. So this is one very simple S to P wave transition, but in general, we can see that same thing because of the selection rule. The transition from NLJ configuration occurs when it occurs to N+1 and L+1 NJ, or L-1 to J. So to same J, one major shell above. This is the mixed configuration that gives the most energy from tensor interaction. Okay. So it's very easy. Now it's very easy to understand. You just make proton and neutron, bring up to the next major shell, keeping the J. And that is giving the big binding energy. So essentially this one, I told you, only in one major cell transition already giving 13, 14, 15 MeV binding by the tensor interaction. Okay, now this is interesting question. Carbon-12 and oxygen-16 cannot be explained by one set of effective interactions. Even if you start shell model, or even you start from cluster model, whatever. But now, it's very important. If you just configure carbon-12 like this, and this is base before excitation. Now, in this case, this nucleons in S state can be excited to P1/2, right? This is exactly what it occurred in helium-4. Now, if you have P3/2 nucleons, then they are excited to D3/2. So this is the main excitation mode that gives largest binding from tensor interaction. So essentially, in carbon-12, all nucleon can contribute to tensor interactions. Okay. Now, situation changes in oxygen-16 because oxygen-16, you feel the nucleon as a zero base configuration. Then those transitions are completely blocked. So you lose that 14 MeV by this. I mean, there was tensor interaction giving 14 MeV by in alpha, this energy, but now you lose that binding energy from tensor interaction. And of course, 14 MeV is not exactly in this case of different configuration. But interesting thing is this one remains there. And in addition, this new P1/2 nucleons can be excited to S1/2. So this is really interesting that you block some part of the tensor interaction, but you gain new tensor interaction energy. And this will continue for heavier nuclei like calcium-48, calcium-40, that it blocks many of the lower excitation, but here you gain also many other things. So essentially, nucleus up to carbon-12, if you increase nucleon number of proton and neutron pairs, you increase the binding energy by tensor interaction, just proportionally. But after oxygen-16, you start to lose some tensor energy. because of this blocking. This is Pauli blocking, so it's natural. And then after that, it's always blocking and opening occurs simultaneously. So essentially, that's a saturation. Tensor interaction saturate because of this reason. I think this is one view of the saturation. There are many other views, but this is one of the essence of the nuclear saturation. Okay. So this is the very important thing. So saturation occurs due to the tensor blocking. Now, so just summarize it. The pion exchange produce central and tensor force. Attraction of tensor force is gained by transition of p-n pair to higher momentum state under selection rule. And tensor interaction is blocked when nucleon occupy higher orbitals, and thus nuclear saturation occurs. And when nucleons in state mixed by the tensor force carry high momentum, about factor of 2 of usual film motion. So you have to include this high momentum nucleon in the wave function. Otherwise, you cannot get the right binding energy from tensor interaction. Okay, so that's a sort of summary. And is there really high momentum nucleons in ground state of nucleus? And actually, I wanted to skip this one because it has been published in several years ago. It's a transition of the oxygen 16, looking at the oxygen 16 ground state. And then there's a high momentum nucleon pair is S equal 1 and T equals 0. So essentially tensor correlated pairs are observed in high momentum that exist in oxygen 16 ground state. And also you know that some this electron scattering, knocking out proton and neutron, they also observe high momentum pairs. I think it's a famous story that is. But today I just want to show this new experiment we just finished. And this is really compare more carefully to the theory. So this is helium-4, and Miki is the main person for this experiment. So I just show very briefly. So how you separate this tensor correlated nucleon and non-correlated nucleon. So you have alpha particle here, and if you should put a proton and pick up this high momentum neutron to form neutron, and then proton is emitted because it had high momentum, and partner is just suddenly removed. This will come out with the original momentum inside helium-4. Now, interesting point is this. When you pick up neutron, if this pair, original pair, is S equal 1, then, of course, residual, those two nucleons should have S equal 1. Otherwise, helium-4 is not spin 0. Okay, so if you observe, if you pick up neutron from S equal 1 state, residual nucleus can be neutron. Now, if you pick up neutron from S equal 0 pair, this doesn't have any tensor interaction. Okay, then this remaining two nucleon, proton and neutron, has to be unbound because S equals 0 proton and neutron pair is unbound. So by looking at the spectrum, missing mass spectrum, if it is bound, it is sure you picked up S equal 1 pair. And if you observe unbound state, then it's S equals 0. And okay, so that's the principle of the measurement. So essentially, if you observe this relative energy of remaining two particles, if S equal 1 particle, it should have neutron and some other continuum spectrum. But if it is S equal 0 state, you should observe this. And this includes the resolution of the detector, but it should be above 0 MeV. So it's unbound state. So by looking at those spectra after neutron DP observation is essentially sum of those two. Okay, but they are separated. If you look at those things, you can see at certain momentum transfer of to the neutron, what is the ratio of S equal 1 component and S equal 0 component. So that's the experiment. So if the tensor force works stronger in high momentum, and so so this is the calculation based on the fraction of S equal 1 and 0 based on momentum, relative momentum. This is the green Monte Carlo calculation. So at lower energy, you see S equals 0 component, some amount. So that's why this ratio is here. But for higher momentum here, it's almost 1 because this is the momentum that tensor interaction is dominated. So essentially, it goes to 1, almost all S equals 0. And if it goes down above, then this central core, repulsive core, gives correlation. And that is independent of the spin. Central interaction doesn't have S equal 1 selection. So this energy is exactly the best energy to see tensor interaction. Okay, so do we see this kind of behavior or not? Is the main aim of the experiment. So this is one easiest to see because the lowest energy and lowest momentum transfer. Just a moment. It's somewhere here. So it's easiest to see this part. You see this is the spectrum, this the observed spectrum. And you see the neutron and unbound state like this. And this higher state may have some more complicated things. So we just fitted data here that essentially this is the tail part of this equal 1, continuum part of this equal 1. And this is the extra thing we need as S equals 0. So essentially we see exactly what expected. Now, question is if you go to high momentum. So this is the plot we observe. It's in higher momentum transfer, it just hit the 1. It's almost all S equal 1 state. So this is little mystery, but the point, important point is definitely at very low momentum, below Fermi motion, that S wave contribute, S equals 0 contribution is there. And at higher momentum, S equal 1 contribution is dominated. We are still struggling with this really quantitative measure of this and what is other effect. But anyway, real tendency is seen consistent with this idea. The low momentum, the ratio is smaller, high momentum, it goes to 1. Okay, so we think that in helium-4, we are kind of understanding this high momentum component exists there. So we have to treat that one. So sure, we see this high momentum nucleons in nuclei correlated by tensor force because we proved it's S = 1 proton and neutron pair. And so then effect of those nucleons on the structure of nuclei near the ground state is expected due to the Pauli principle or tensor blocking effect, as I showed. Now, how is it in asymmetric nuclei? This is the interesting question. So now, if you see the nucleus, I just colored it. Now here, this is symmetric, so-called symmetric. So those are in same measure. Proton and neutrons are all in measure, same measure shell. This is also. But when you talk about the neutron-rich nuclei, that in this case, protons are in one major shell, and neutrons are distributed in 2 major shells. And this is again, here is more shells are filled. So essentially in this green place, that neutrons are occupying one more higher major shell than proton. So that what happens if such kind of condition occurs? And the problem always occurs there near the border of those places. Okay, now just to remind you that those things are giving energy, and it gives already 14 MeV in one major shell. That is important. It's just the nuclei we are now discussing is essentially neutron-rich nuclei. Almost all of them, except some of them, are just one major shell different. Okay, we don't reach 2 major shell different nuclei yet. That may be another interest over there. But now, so one major difference. So you are changing this. Okay, so if I just write oxygen 18, do you remember oxygen 16? Oxygen 16, blocking start to occur, but those are opening new tensor interaction. But in oxygen 18, because you feel neutrons in next major shell, everything is blocked. So here, essentially, you have no tensor interaction gain to the binding energy of oxygen 28. You are losing 14 MeV from here, some MeV from this transition, some MeV from this transition. So essentially, your potential depth changes. All binding energy changes this amount. So that's why oxygen 28 really lose energy and cannot make doubly closed. This is a difference of neutron-rich nuclei. And stable nuclei. Okay, so it's become very simple to ingredient, mean field and this L equal 1 the tensor and blocking occurs. Now, how much this blocking occurs? If you block one transition of one pair, how much does it? So in helium, well, this about 5 MeV, and oxygen 22, 2 MeV, 24, 2 MeV. So of course you have to count how many pairs are blocked. So you have to multiply by that. So just the energy, I'm just giving you, there's only a few MeV change occurs because of this blocking. If you just block one pair, okay. So I mean, with a number, it's very difficult to explain. So I just explained why helium-10 and oxygen-28 are not bound. So essentially in helium-10, you feel P1/2. So then this transition of S wave to P wave is completely blocked. So you cannot gain. And actually, if you see this Wood-Saxon potential, usual Wood-Saxon potential diagram, that P wave is here, P wave at mass here must be bound. P1/2 is in usual potential is bound, but then helium-10 has to exist. But because of this, you lose energy, tensor energy, by this amount. And so this is the point of helium-8. Then you go up here, it becomes unbound. So by losing this tensor energy, so if you put nucleon here, it's go up and you cannot make bound state. Now, oxygen-28 is exactly the same. You block this one and this one, and it's from D wave is D3/2 is in usual potential model is bound, is still bound, but just because of the loss of the binding energy by tensor, it become unbound. Okay. Now, then why calcium-48 is magic and bound? It's same thing, right? One neutron-rich doubly closed shell. Now, if you see the place of calcium-48 neutrons are increased in F7/2 shell. Now, this is interesting. F7/2, 7/2 doesn't exist below. So this is the highest J appeared in the shell. So that this state is not used by the tensor interaction at all from the beginning. So all the transitions occurs from here to there, 3/2, or 1/2, or 5/2. So this tensor interaction that bound calcium-40 all is there. None of those tensor interaction in calcium-40 is blocked. None of them are blocked. That's why still this calcium-48 is bound. So essentially, this is very important thing. Always J upper, largest J upper orbital is not contributing to tensor interaction. And that's why this kind of funny thing occurs. Okay, so this is really essence. I'm going just the example of those things. It's just the same thing. But now if you start to put some particle in P wave and such things, different thing occurs. And that's why this shell gap, F7.5 to P shell gap is large. Okay. Now, so this explains the first, my biggest question of lithium-11. So lithium-11 is considered as lithium-9 core plus 2 neutrons. But this lithium-9 has its own structure with tensor interaction. So now this is the lowest 0 particle 0 hole configuration of lithium-9. Of course, there are some pairing interactions and some other interaction. For example, it's excite those two pair. In this case, it's S equals 0 pair up to P1/2. This is mixed. And then tensor interaction is from S wave to there. I include this because real calculation is done, including all of those. Okay, so this part is giving binding, part of the binding in lithium-9. Now, you want to add 2 neutrons in lithium-9. And in this case, S wave is pretty high, I mean, next major shell. If you put neutron in P1/2, one is that you also block the pairing interaction because it's completely filled and closed shell, no pairing interaction. So this one loses the energy. Also, if you put particle in here, tensor force is blocked. So this is important. You can, if you put 2 neutrons in P1/2, you lose energies from pairing and tensor interaction, both. Now, if you put 2 neutrons in S1/2, then this tensor excitation is not blocked. And pairing is not blocked, but originally this gap is large, so this effect is small. Okay, but anyway, the point is that the P wave configuration blocks the tensor energy, and S wave configuration doesn't block tensor interaction. And as a result, those total energy of this total wave function become very close together. It essentially, it's calculated, it become almost same energy. That's why this configuration and this configuration are mixed equally. So that's the basic reason why lithium-11 halo has mixed wave function of P wave and S wave. And this is the only really the microscopic explanation why P wave and S wave is mixed in here. Just a moment, I have to check the time, right? Oh, I'm almost done. Okay, so this is the most important thing. I come back and if I have time, I could show you more example, but I just skip more example is the other magic number can be explained with same mechanism. And why magic number disappeared can be also explained because, for example, 20, magic number 20 disappeared because of the blocking of these 3 half, it become very close to this one, and P wave become much closer. So that kind of thing occurs, and okay, there's some other things. So essentially, I just skip and conclude. So tensor interaction importance is reviewed, and the effect of recently observed high momentum p-n pair are considered in relation to the nuclear structures, and importance of tensor blocking that is significant in neutron-rich nuclei are discussed. And new model of this tensor blocking I call is introduced, and then examined those all new behaviors of neutron-rich nuclei. I think we can explain many things from one principle of this tensor blocking. So I think that all of those questions could be answered. So just it is related to some other things. So if you consider that because you lose tensor energy if you go to neutron-rich nuclei, so neutron drip line may be closer than present predictions. Present predictions doesn't include this high momentum blocking effect of the nucleon interaction. So there could be a chance that drip line may be closer than present predictions. And next magic number is 56 and 58. And of course, those are other things, nuclear astrophysics and those things. And one thing is skipped and hide in this talk is the relation to the LS interactions. We know that half of the LS interaction in nuclei come from tensor interaction. And this movement of the shell is very similar to the LS interactions. So it's not really a relation between phenomenological LS interactions and this tensor blocking effect has not been discussed. But I think this must be a very important question that we have to solve in near future. Okay. And each things you may find in those references. And sorry, I spent a little longer time, but thank you very much for your attention.